All right, so today we're going to start talking about antiderivatives. So in English, whenever we put the word anti in front of something, it means sort of the opposite of, right? So you guys know what you do with derivatives, and we're going to start with that right now. So you've got this note sheet, and I've got your function written on one side, and then we're going to write the derivatives that you know and love on the other side. Hey guys, I heard. That's fine. We're starting on 4.1 today. So grab your sheet out. I'm going to let you have just a couple minutes to fill these in. You should know the derivatives for every single one of these rules. These are all the derivative rules we've done so far. So go down this list, this entire front sheet of your notes, and fill in the derivatives, okay? So nothing new at this point. You're just filling in what you remember from the last couple of chapters that you've worked with. All right, so let's fill these in together. What did you get for the first one? What is the constant rule? What is its derivative? Right, so this is y prime equals 0. How about the linear function rule? When you have a line, what is its derivative? A. It's the slope, so the value in front of the x, right? Remember, derivative just means slope, and when you've got a line, the slope simply is the a value on that one. How about the constant multiplier rule? What do we do when we have k times f of x? Right, we just have that k, that constant multiplier, come along with the derivative of the part that has the x in it, so f prime of x. How about sums and differences? So we just take the derivative of each piece and put them back together with the addition or the subtraction that the problem started with. How about the power rule? N times x to the n minus 1. All right, did everybody have all those correct? All that looks good? Okay, we're going to do the trig rules next. So then what is the derivative of sine? Cosine, good. The derivative of cosine? Negative sine x. Good. How about the rest of them are the ones that we use a little less frequently, so it's sometimes more difficult to remember. What about the derivative of tangent? It's secant squared. You might be remembering 1 over cosine squared or something like that from a different point of view maybe. Our book actually uses it as secant squared. How about the derivative of secant then? Secant tangent or tangent secant, yeah. So secant x, tangent x. And then cotangent and cosecant are very similar to tangent and secant. If you know one, you probably know the other. You do, in fact, get negatives. Anytime you take the derivative of something with co in front of it, you get a negative. So this will be negative. What's the derivative of cotangent? Right, negative, and then the cosecant square root of x. And then again, when we do cosecant, we've got a negative, and then the derivative of the cosecant part would be? Right, the rest would be cotangent or cosecant cotangent. Oops. Secant x, cotangent x. So you might be thinking, well, okay, but I already knew all of that, and I hope you did. I hope you had all those written down correctly. What we're going to do now is basically we're going to start on the right-hand side of this list and think, what would I have had to have done to get there? And we're going to go backwards. Okay? So what we're going to do, the notation, we're going to let capital F be the antiderivative of f. So before, when we took a derivative, we introduced this notation of doing primes, right? Well, what we're going to do now is we're going to basically be starting with something on this side, and it's going to be a lowercase, and when we go backwards, so to speak, we're going to call it an uppercase. Okay, so uppercase means antiderivative. The indefinite integral of f with respect to x on the interval I is defined to be, so this is new notation if you haven't had a calculus class before. This is it looks like a really tall and skinny s. I mean, that's what it looks like, right? That's an integral symbol. The integral of f of x dx equals capital F of x plus c, where c is an arbitrary constant, and it's called the constant of integration. Now let me identify for you some of the pieces here and how we say them. So like I said, this is the integral, or you can say the antiderivative The dx at the end must be there. Okay, don't leave that off. This tells us the variable to integrate. And I know in what we're doing right now, it feels like that just is a little bit silly, but the reality is as calculus keeps moving, we start working with variables where there's multiple variables within one function. And so it becomes very important to know which one's the variable right now. So we use that notation to indicate the variable that we are going to take the antiderivative with respect to. And then the reason that we have this plus c on the end, which feels a little bit awkward, is because think what happens. If we were to start with this side of the equation, what would happen if you took the derivative of the c? It would be 0, right? It would go away. So there's always the possibility that there's plus or minus some number that we could have had that when we took the derivative of it, it went away. So we always have a plus c on the end of our antiderivatives when we're working with indefinite integrals. Now in a couple of sections we're going to work with definite integrals and you'll see something slightly different happen. Okay? So the next thing we're going to do then is we're going to take a look at the antiderivative rules. All right, so think with me. You're in your mind, you should be thinking, I want to go backwards. What would I have had before if this were my derivative? So in other words, you're thinking, these are derivatives. If these were the derivatives, what would the original function have been? Okay, so first of all, we're going to use capital letters on all these, so use capital Y's for these, all right? What would the original function have been if I took the derivative and I got a 0? Some kind of a number constant, right? We're going to use c on all of ours. C's and k's are used often for constants, so we're going to use the c. You can see the next one they use a k on, right? Y equal k. So the constant rule, what would have had to happen when we took a derivative, we got a constant? What was it, Christian?
Kx.
We would have had to have a kx plus c, right? Because if I took the derivative of c, it would go away. Now, the next one's not an exact match from what we did before, but it's awfully similar. What do you think is going to happen if you have a constant multiplier? Yeah, the constant multiplier just gets to be there for free, and then what do you think will happen to the small f of x? It'll turn into a capital F of x, exactly. And then what do we need? Plus c. We're going to have a plus c on every single one of these, okay? What do you think will happen for the sum and the difference? Something very nice. What should it be? Yeah, it should be the same thing. Go with the capitals, right? The antiderivative, and they're joined with the plus or minus. And then I've run out of space on my line, but there's a plus c at the end of that. All right, power rule. This is the first probably interesting one. So let's think through what we do when we have a power rule and we take the derivative. So when we have a power rule and we take the derivative, we take the exponent and we bring it down as a coefficient, right? So the exponent becomes a multiple. Like you multiply it. So what's the opposite of multiplication? Division. So we're going to divide this. Again, when you took the derivative, you used the current exponent. All right? So we're going to use the increased exponent, one higher. So this looks like x to the n plus 1. We should have an exponent 1 larger, because if I were to take the derivative, it would decrease, right? So this is increasing by 1. And we can divide by the new exponent instead of the old exponent. Everything's backwards. Using the new exponent instead of the old exponent, I'm adding 1 instead of subtracting 1. I'm dividing instead of multiplying. And then I need plus c. Okay, so far so good. Next is trig. Now here's the cool thing at this point in this section about the trig. What do you notice about these trig functions? They're all the derivative forms, right? Yeah, we're going to get to the other ones later, but it's a different section. These are just all those same derivative forms you've seen before, but they're the function now and we're going backwards. Now you have to be a little bit careful, and I will tell you, in all honesty, I always remember the derivative of sine is cosine, and then I have to stop and I have to think when I do antiderivatives or when I do cosines, when I get negatives and when I get positives. So obviously sine and cosine switch. I mean, I know the sine is going to become a cosine, but then I have to think, do I need a negative on this? Well, if I were to start with cosine and I took the derivative, what's the derivative of cosine? Negative sine. So I do need a negative on this, or it's not going to work. And then I need the plus c on the end, of course. All right, so let's do cosine then. So obviously going to be sine. Do I need a negative? No, because the derivative of sine is cosine, which is what's on my left-hand side now. And then I need a plus c. Secant squared. Whose derivative is secant squared? Tangent. Is there a negative on that? No. Because, oh, not tangent squared. Let's say it right. Write it down right. Tangent. Because the only ones who have negatives are the ones who have antiderivatives that would be cos, right? Tangent is not a co. Secant squared is not a co either, for that matter. All right, secant tangent. What's that one going to be? That one is secant. Oops, I forgot my plus c before. Y'all didn't tell me. All right, let me put the plus c on this one as well. Do I need a negative? No, because it's not a cofunction, right? How about cosecant squared? Whose antiderivative, I'm sorry, whose derivative is cosecant squared? Yeah, that one's the cotangent of x, and it is negative because when I take the derivative of cotangent, I get negative cosecant squared. The negative's not on the cosecant squared right now, right? So the negative needs to be on the original function. And of course, I need a plus c. Last one. Cosecant cotangent. That's cosecant, and it's negative. You got it. Negative cosecant x plus c. All right, so these rules right here are all that you need to know, and I'll double check on whether you need to know the secant, the tangent. I think you actually need those as well, so we'll get to those shortly. But these rules, plus just 2 or 3 more, I think it's 3 more, maybe 4. Yeah, it might be 4, are all you're going to need to know for your antiderivative quiz next Monday. Okay? That's it. Those simple rules. And they're all just backwards of what you've done before. So what we're going to do right now is we're going to go through and we're going to practice some of these rules. All right? So we've got a 2x here. So I need to do what? What would the antiderivative of 2x be? Okay, 2x squared. Divide by 2. So we increase the power by 1. That's why it's squared now. And we divide by the new power. All right, how about the other one? What about the 3x squared? 3x cubed divided by 3. And then what do you need? Plus c. Plus c. Now, if you were on the antiderivatives quiz next Monday, you would leave it that way and you'd be done. All right, but clearly you can see for the purposes of these problems, there's simple cleanup that we can do on this one as well. So we are going to clean this up. This is going to be then x squared minus x cubed plus c. So in your homework, you are going to do the cleanup for these. Does that make sense? Okay, what is different about number 2 than number 1? It's a fraction. Can we write it differently so that it's not a fraction? Yes, and that's a good place to start. So how could I write this differently? X to the negative 6th, and then minus 2 dx. Anytime you rewrite the notation, remember the dx. Okay? What in the world would I do with x to the negative 6th? Minus 5, right? So every time we start working with negatives, we have to be real careful, right? Adding 1 is actually going to make this negative 5. And then I would divide by negative 5, right? Good. What in the world am I going to do with that negative 2? It's negative 2x. And again, if that's sort of looking a little bit funny, remember, I should be able to go backwards. If I start with negative 2x and I take its derivative, do I get negative 2? Yes, so I did it right. And then we need a plus c. Again, for your quiz next Monday, we can leave it right there. But what about this does not look quite so friendly, or at least not look quite like what it started out as? The fraction part of it, what's not like how it started? How is it different than how it started? the exponent is negative, right? I did not start out with any negative exponents, so I don't want the problem to end with negative exponents. How do I fix the fact that this has an x to the negative 5 in it? Yeah, so we take it down. You guys want to... Okay, so the negative 5 is going to still be negative 5. You can either leave the negative down the denominator or put the negative in front. It doesn't matter. And then the x to the negative 5th will be in the denominator now as x to the 5th. And then minus 2x plus c. Now, I'll remind you again the next couple of days, but my suggestion when you take the quiz next Monday is to write yourself a note at the top of the paper. What do you think the note might say? Don't forget the plus c's. I had a student take that quiz the very first time that I gave it, and he missed his plus c's on every single problem. And he got a 0 on the quiz. He retook it, obviously. He had them all right other than that, which means he missed extra credit, right? Because he actually knew the rules, but he forgot the plus c's. So you want to make sure those don't get left off. I know I'm that mean teacher. I'm okay with that. I'll keep that reputation. All right, what about this one? This one looks weird. What's so weird about this one? There's a square root, right? It's also in the denominator, right? How am I going to change this to use the rules that I have? Because this does not look like the rules that I have, right? What am I going to have to do? So what would you like to do, Edgar? Okay, so if I do that, then I'm going to have x to the negative 1/2 over x. There's nothing wrong with that except that it still is not complete. Is there a different way that I could reword this so that this cleans it up a little bit better or a little bit more?
X to the 3/2.
Okay, let me try that. So I could leave this as x to the 1 and then the x to the 1/2 right here like this, which would be x to the 3/2. You can get there from the other direction that you're mentioning as well. Right now I'm just doing revisions of the writing of it, so I haven't really found any calculus yet. This is just algebra. But again, I still have it in the denominator, so at this point I would probably bring it up to the numerator instead of doing it at the beginning. So I've got negative 3/2 x. I'm sorry, x to the negative 3/2 dx. Is that okay with everyone? Just rewrite it in several different ways. We want the x's combined. That's one issue, right? We definitely need the x's to be combined. We also need them to not be in the denominator. So those are sort of two things that we're trying to attain before we move forward. All right, so now I'm going to, what? Take an antiderivative. So what's it going to do?
X to the minus 1/2.
Okay, so we're going to increase that exponent. So if I have, let me write it a little bit further over. If I have a negative 3/2 and I add 1, I get negative 1/2. And then I would divide by negative 1/2, and then plus c. Again, on your quiz on Monday, that looks great, but it really doesn't look all that great. What are some things that I'm going to need to do to change this up to make it look actually more like the one I started with?
Put the x back on the bottom.
Okay, we're going to put the x back on the bottom. Is there anything else? Sorry, I left that negative there. There's no negative there. All right, 1/2 there, just like that. The x to the 1/2 can be written as a square root. That's true. Anything else?
That two can go up.
The what can, Christian?
The 1/2.
Yep.
So 2 can go.
All right, so maybe like this. Would that be okay? Okay. Remember, this is basically, not basically, it is, division by 1/2 is the same as multiplication by 2, right? Or you can think of it as I'm going to multiply the top and the bottom by 2 to get rid of that 1/2 in the denominator. And then the negative can go either place. You can put the numerator, denominator out in front. Any of those actually will work. So we do end up with this as our value. Now, occasionally I'll have somebody who will ask questions about rationalizing denominators. We don't need to rationalize anything, remember, because we don't know what x is. Depending on the value of x, this actually could be a rational number. Okay, so we're not going to deal with that. We're going to leave it just like this. Number 4. What is different about number 4?
There's multiplication.
There's multiplication. Do we have a rule for multiplication so far? No, we do not. In fact, you won't this semester. For those of you who are going on to a Calc 2 class, it isn't until Calc 2 that you start dealing with what happens when I really do have multiplication. And it's a lot trickier than multiplication with derivatives. So what are we going to have to do since I don't have a rule?
Multiply it out.
FOIL it, multiply it out, right? So we're going to multiply everything out. The first term's x times 3x would be 3x squared. Outside, x times negative 2 would be negative 2x. Inside is positive 3x. And then the last terms is negative 2. And if I combine those middle terms together, I have plus x. Now technically, that should be in parentheses. If you don't put those parentheses there, it's not a huge deal. People start to get, in mathematics, we start to just drop parentheses on that one quite frequently. Let's actually take a look then at the antiderivative for 3x squared. What would that look like? 3x cubed divided by 3. So we increase the power by 1, divide by the new power. How about the plus x?
X squared divided by 2.
X squared divided by 2. And then the minus 2?
Minus 2x.
Minus 2x.
Plus c.
Thank you. Plus c. And this one requires very little cleanup, but there's one piece I can clean up. What would the final answer look like?
X cubed.
X cubed plus x squared over 2, or you can put 1/2 x squared if you'd like, minus 2x plus c. Any questions on that one? All right. 5. Oh goodness, we got some trig in this one, don't we? Okay. So let's start with the piece that's not trig, the 1. Antiderivative of 1 is x. Okay, so that's fine. And I'm going to have this piece which says negative cosecant cotangent. So cosecant cotangent. What is the antiderivative of cosecant cotangent?
Cosecant.
It's cosecant. And I need a negative in there actually, correct? And I actually already have a negative in the problem, correct? So what's this going to become? Is it going to be minus cosecant or plus cosecant? Plus cosecant. And again, the easiest thing to do is to look at it and decide, if I take the derivative, do I get back where I was? Cosecant, what's the derivative of cosecant? Negative cosecant cotangent, which is what you had. And what else do I need? Plus c. And there's absolutely nothing to simplify on this one. That's friendly, right? All right. Number 6 does not look quite so friendly where it starts out. Any thoughts on what we might do to make this doable? Because right now it's not doable. It's not in a form that we can do anything with. Oh, so Edgar's remembering a property of trig. Can you say it a little bit louder for me, Edgar? The denominator is equal to cosine squared. Do you guys remember that Pythagorean identity? It says sine squared plus cosine squared equals 1. And if you were to solve this for cosine squared, you'd get 1 minus sine squared, right? So that is in fact my denominator, and I can rewrite it as cosine squared. Why in the world is that helpful? There is a reason, very good reason why that's helpful. What is friendlier about the way it's written now than before?
It's 1 term instead of 2.
Yes, the denominator has 1 term. There's no addition and subtraction in the denominator, right? Okay, there's really no problem with addition and subtraction in numerators because you can separate fractions. But when you have addition and subtraction in denominators, you can't do that. So that's a problem. So this is friendlier for that reason. Now, it's still not completely ready to be worked because I still have sines and cosines and division. So any thoughts about what I could do next? Oh, maybe I could. So I could write maybe something like sine x, cosine x, cosine x, something like that. Edgar, does that look, or sorry, Christian, does that look okay? And then this one you recognized as being tangent. What would the other one over here be? I mean, I still don't really want, I still don't really want a denominator. This is tangent, because sine over cosine is tangent. And this is really 1 over cosine. And 1 over cosine is secant. And I have already done something that I told you not to do. Does anybody catch it? I left off my dx. Let me put those back in. Tangent secant, that's friendly. Why?
Because there's no division.
There's no division. That's true. There's also friendly for another reason. Yeah, we actually have that as one of our specific flat-out rules, right? It is the derivative, like you said, of secant. So the antiderivative here is secant x plus c. Thank you. And while the simplification was required a whole bunch through the process of getting it to the point where I could do the antiderivative, there's no simplification when I'm done. Okay, we've got one more problem, and it has one additional step, one additional piece of information that allows us to do one additional step. So let's take a look at this one. This one tells us to find the function f of x, satisfying the given conditions. And notice they changed the notation. They actually wrote this as f prime and asked you to find f. Okay, so it's the same thing as writing this as f and asking you to find capital F. All right, so they've notated it a little differently. But what else is different besides that? That's just a notation difference. There's actually something uniquely different here.
It gives you an x value.
It gives you a xy value, right? It actually gives you a point on this curve. You might think, well, why does that matter? Well, what this is going to allow us to do is it's going to allow us to find c. We're not going to have a plus c when we're all done with this problem. We're actually going to be able to figure out what c is. Okay? Now, we don't start there, of course. We're starting the same place we did with the last problem. So we're going to find the integral of 12x squared plus 2 dx. So, what's the antiderivative of 12x squared plus 2 dx? 12x cubed, divide by 3, good, and then plus 2x, very nice, plus c. And this is actually my function, right? This is f of x. This would be what we would call a general antiderivative. It's called general because it has that plus c on the end. And all that plus c on the end does is it takes the whole graph and it moves it up and down. Do you remember that from algebra? Plus c is just a shift up and down. And the reason that that works is because if I shift it up and down, that doesn't change the slopes of anything. That's why the derivative is still the same. So what we're going to do now is we're going to actually be able to find c. How? Yes, by plugging in 1 and 2 for x and y respectively. So from up here, I know that x is 1 and f of x or y is 2. So I've got 2 on the left equals 12 times 1 cubed. Actually, we could simplify the 12 over 3, couldn't we? Can I just do that? All right, 4 times 1 cubed. That's 4. And then plus 2 times 1 plus c. Okay, so what do I have on the right-hand side with that c? 6. So what does c have to equal? C would have to be negative 4 for that to work, right? Or subtract the 6 to the other side if you prefer. Now, please be sure to answer the question asked. The question said find the function f of x, not just figure out what c is. So we actually are going to write out the function with the c plugged in. And you won't do any of that for your quiz on Monday. It won't be any of those. It'll just be the steps before. Okay? Any questions on that one? All right.